Hi, everybody. We are talking about unicorns today, and we're talking about how to tame a unicorn. No, I'm not going to tell you how to hold a unicorn as your pet. Sorry. So whoever thought I'm going to talk about that is free to leave now. Okay. No, we're going to talk about how to tame a unicorn or ducks. I have 4 ducks, so I even could tell you something about that. Or about bicycles, or about rainbows. Actually, we're going to talk about how to handle any character out there. Before I do that, I give you a short introduction of myself so that you know who I am. I'm Andreas. I'm working as a workflow integration specialist in a German publishing company. I'm co-organizer of the PHP-Usergroup in Frankfurt. I'm the person behind PHP.ug, whoever heard of that. If you didn't hear of it, have a look. It shows you your nearest next local user group. I do maintain some open source libraries, contribute to open source and stuff like that. But the main thing is I'm German. And as Germans, we have some special characters. And all the fun I had with these special characters, I thought I would want to share that with as many developers as possible, so that you don't need to get into those nitty bits that I had to go through. Before we go into handling these things, we need to define some things. Who of you knows what a glyph is? Okay, some people? Fine. For those that don't know what a glyph is, this is a glyph. This is another glyph, and this is one. And these 3 are, even though they might look the same, they are different. So a glyph is a representation, a visual representation of a character. The character is the A, and how the A looks on your screen or on your paper, that is a glyph. And multiple characters, if you combine multiple characters, A, B, C, D, E, F, G, and so on, into one set, that is a character set. So a character set contains all the characters, or is a collection of characters that is used by multiple languages. So, for example, the Dutch language and the German language and the British language, they all use the same set of glyphs, the same set of characters. One of these character sets, most of you know, is ASCII. This morning in the keynote, we heard that in 1969, the first computers were connected with one another. One of the requirements for that was a common character set, so that each of these computers could understand each other. We come to that later. Another one is ISO 8895-1. Who of you has heard of that? I probably should ask who hasn't heard of that. Unicode also is a character set. Unicode is a character set that supports all languages, all current languages, all historic languages, and it will support all future languages. So that's a character set. But we also need an encoding, because we are talking about machines here, and machines, well, they don't know what an A is. A machine can't understand an A or a B or a C. They only understand numbers. They're just number crunchers. So we need a way of translating this character, not the glyph, the character, into a number. And that is the encoding. One encoding is ASCII. Another encoding is ISO 8859-95. And the third encoding is UTF-8. Morse code is a character set as well, an encoding as well. It encodes a character into a representation that can be sent somewhere else. Another one would be the semaphore alphabet. Who of you knows the semaphore alphabet? Okay, it's the flag alphabet that is used on ships. I thought I'm in the Netherlands, someone would know that. So the character set is not necessarily the same as the encoding. It was, but it is not anymore. And we come to the details about that in short time. Before we come to the details and how it works today, we need to know some historic details. I told you I'm going to go into detail on ASCII. ASCII is the American Standard Code of Information Interchange. That was created in 1963, so 6 years before they connect those few computers. Because at that time, it was clear we have to have a common coding, a common character set that all the computers could understand, because they were starting to connect different computers with one another. Before that, it was just, here was a computer, there was a computer, there was a computer, and they all had their own character set, depending on the manufacturer. IBM still does that until this day. They call that EBCDIC. I'm not going into detail on that one. So what does ASCII look like? ASCII is, well, okay, we need some uppercase letters. We need some lowercase letters. Some numbers would be cool as well. And we might need some special signs like interpunction and stuff like that. And, well, we also need some very special things like the bell character. So if you hit something that the computer can't understand, your terminal that is directly connected to the computer can bell and can give you a signal, I can't understand that. Or the line feed or the carriage return or the syn and ag information. That is all encoded into this ASCII code. And in those early days, memory was limited. So to have all this information in a character set, people said, okay, we use 7-bit. 7-bit is completely enough, 128 characters. Hey, that should work out. It does work out in America. But, so if you say, if you check and do an echo of hello world and pass that to hexdump, you will get this weird characters, these weird numbers. That's the, well, the hex representation, the binary representation of the string. So that is how the encoding works. It gives you the string, and then that string is translated into bytes, bits and bytes. Fine, cool. And then the British people came into play, and they said, you know what? We want our pound sign. And some others said, we want some special signs as well. And then we Germans came along and said, what about our umlauts? Or the Danish people and the Norwegians wanted their special signs as well. And so a lot of other nations wanted their special signs as well. And, well, okay. It's a bit messy, but ASCII was 7-bit. By introducing an 8-bit, we can get another 128 places to put characters on. And I mean, sorry, but that is fair enough, isn't it? I mean, for me as a German, that's okay. My umlauts are in there. Cool. Yes. What about the Greek people? Well, that's okay. That's easy. Because, I mean, okay, the Germans and all these Western Europeans, they can use their own code encoding. And for the Greek, we just do a different encoding. We just use the ASCII standard, and those second 128 code places, we put their Greek characters on there. And that's cool. Okay. And that was the point where the ISO 8895 was created. It's ASCII compatible. The first 128 characters are the same throughout the ISO character sets. And then there is the ISO 8895-1 for Western European languages and ISO 8859-2 for Central European languages like Polish and stuff like that. And the number 3 for Southern Europeans, so Spanish, for example. And the number 4 for Northern European peoples, that's Scandinavia and stuff like that. And number 5 for Cyrillic, and 7 for Greek, and, well, a lot of others. You might know that under a different name. For example, in Windows, it's Windows 12.52. There are some differences in the first 32 characters, though. There is Latin 1, some of you might have heard of. And there is IBM 819, and there is CP 819, which translates to code page 819. But we have to be careful. We have to be very careful. If we take one of these characters, it's just one as an example. It has a hex representation of C4. C4? C4, yes. And this hex representation is a German uppercase A, German Umlaut. Perfect, at least in ISO 88591. If I use a different encoding, that same character or that same encoding suddenly gets something completely different. And this is an Arabic sign. This is a Greek sign. And this is, I think it's Thai. I have no idea. And I can't even tell you how that sign is named. No idea. It is all the same binary representation, but in the end, we don't know what sign or what character it is, what glyph we should use for that. And the worst thing that can happen is you use an encoding where that isn't even defined, which might happen in, I think that is Hebrew. And okay, so we have 128 plus 128, it's 256. Perfect for us. What about Chinese? I think in China you need to know about 3,000 different signs to be able to read at all. So that's about primary school level. And what about Japanese? What about Korean? There is no way of handling that in an 8-byte character sequence, on 8-byte characters. And so very early, the question was raised, wouldn't it be cool to have all the characters in one character set? And that's where Unicode comes into play. Unicode is a character set, not an encoding. Unicode is ISO 88591 compatible, which means if I have an ISO 88591 character encoding, if I have a character encoded in ISO 88591, that is the same binary representation also in Unicode. I'll show you what I mean later. It's ASCII compatible because it's ISO 88591 compatible. And the first version was introduced in 1991, and it had 65,536 code points. Over 65,000 code points instead of 256. Isn't that awesome? By coincidence, that was the same year that Java has seen the light of this world, and they made a mistake on that. I'll tell you about that later. Soon, the Unicode consortium realized 65,000 is not even enough, because if the idea is to have all the characters of all the languages that are currently spoken and the historic languages in there, that won't be enough. So the version 2, which was introduced in 1996, already had over 1 million code points. That should work out for a number of years by now. And then the next really, really important step was in 2010. So we have 19 years until 2010, and in 2010 emojis were put into Unicode, and that was the point where everything changed. Because now people are desperately waiting for the next Unicode version to be released, because then we have 16 new emojis. Okay, we also get 3 new languages, but who cares? So how does Unicode work? It's pretty easy, actually. Unicode defines 17 so-called planes. Each plane has over 65,000 code points, and each code point is defined by 2 bytes within the plane. There is also a private use area defined, so you can even define your own characters within Unicode. Though then you need to tell people what characters you have at certain code points. Who of you knows a perfect use for such a thing? Yeah? Exactly, exactly. That's, for example, this private use area, for example, is used by, thank you, Font Awesome. Font Awesome uses this private use space to define their symbols. So if you have something like that, you don't need to file a request to the Unicode consortium. I want my character in there. You can just use that private use area. And the most commonly used characters are within the first plane. Yes, we had that. And but there are multiple ways to describe a character. To handle that, Unicode internally has a way to handle normalization. So if I use two different ways of describing a character, for example, the end with a tilde from Spanish, from Spanish character, from the Spanish language, that can either be represented by one character, end with tilde, or I can combine two characters. I can combine the character, the end character, and the tilde character. So I have two different ways of describing this one letter, and there are actually within the Unicode definition certain ways of normalizing that, so that I can compare different texts, and even though those two texts might describe this n in different ways, I still can compare them and get the same results. And there are also multiple ways to compare such characters. Comparing characters is called a collation. Different reasons for collations are, for example, for me as a German, if I have a name with an umlaut a, I expect that to be sorted somewhere within the a characters. So I have a. Perfect. For example, the A with a circle on top of it from the northern alphabets, they expect this A with a circle on top of it not to be sorted within the A's, but they want that after the Z. So different information there. So I need to handle that as well. There are also rules within the Unicode set that define that. So this is what the first plane in Unicode looks like. Looks weird, doesn't it? Yeah, it's easy. Let's have a look at that. This is ISO 8895. So everything we know, there are always 2 bytes for a character. So everything that starts with 00 and then, for example, A4 is, for example, an A. That's here in the first plane. That's the ISO 5895, 59. And all the others are different other information. And if we have a look at what is this here, this huge thing here, that's the CJK characters. That's the Chinese, Japanese, and Korean characters. That's a whole bunch of stuff, isn't it? And, okay, oops. And here we have some other East Asia scripts. That is awesome. And everything within the first plane, everything within one character set. That's cool. Please take a special note on these few things here, D8 to DF. We come to that later in combination with Java. And this is the part for the private stuff. That's what Font Awesome, for example, uses. Are you with me still? Yeah? Any questions up to that point? Okay, so an example. This is an A. Sorry, it was not A1, it was 41. So if I want to encode an A in Unicode, it's U plus 0041. Well, U plus is just, okay, it's a Unicode character. If I want to use this N with a tilde, I can either use 00F1, which is this one character, or I can combine 0063, which is the N, with 0303, which is the tilde on top of some other character. Wrong direction. This one, that is a Thai character, which is OE04. Does anyone know how it's called? No? Sorry. Or you can use this emoji, which is O1F4A9. Oh, wait a minute. That's not 2 bytes, that's 3 bytes anymore. Yes, because the first byte, in that case, the O1, tells me it's not on the first plane, it's on the second plane. And remember, we have 17 of these planes. So as soon as I have a character from the first plane, that's perfect because I just can skip the OO in front of that. And then I can use the position on that plane. As soon as I have something from one of the other planes, I, of course, need to tell the computer which plane is it on. In this case, on the first plane. And there are even 2 ways of describing this emoji. I could also describe it as a combination of the 2 characters of the character that is on D8 3D and combined with DCA9. I tried to find out what those single characters are, but I couldn't find a combination why that gives that emoji. No idea how that worked. Yes. Unicode is Unicode. It's a character set. It is a character set that by default uses 3 byte. But it's not an encoding. The question is, how can I encode this, the different code pages, or the different positions on the code page, into something a computer understands? Well, there are at least 3 different ways. The first one is, learned something new, awesome. The first one is UTF-32. UTF-32 means I have 32-bit, so 4 byte, to describe a character. Yeah, it works perfectly. I have 2 zeros at the beginning, always, because I only need 3 bytes. And then I have, most of the time, 2 zeros as well, because usually I'm encoding something from the first plane. And then I have some payload. So it is very, very memory intensive. And you pass around a lot of zeros. Nah, we don't use that. The next possibility would be UTF-16. UTF-16 is cool, it's 2 byte. That works perfectly on the first plane. As soon as I want to encode something from one of the planes behind the first plane, I come into trouble. I told you about Java. Java was developed at around the same time as Unicode, 1991. And the second version of Unicode was finalized in 1996. At that time, Java was well established. So at the beginning, they only had 65,000 code points. And the Java people said, hey, you know what? 65,000 code points, that's 2 byte per whatever. So just use that as our internal handling. So they use UTF-16 to handle everything internally, which is cool, as long as you don't use anything from the other planes. UTF-16 has a way to actually handle that. So UTF-16 is not always a 1 byte per character language encoding. There might be 2 bytes per character. I'll tell you about that later. And the third option you have is UTF-8. UTF-8 is really awesome because it's between 1 and 4 byte per character. But for those bytes that have a lot of zeros in front of it, we only use 1 byte. And if we have something with more information, something from the upper planes, we use more bytes, but only as much as we need. So it's very space consuming. It's very space efficient. And that's cool. So how does UTF-16 work? UTF-16 usually is 2 bytes, always on the first plane. It's used by Windows internally, by Mac OS, by Java, but it's not stream safe. I'll show you in a short time why. And there is also always the question, which is the first byte? Is it the one that comes first in the stream, or is it the one that is the second in the stream? That's why you always need a so-called byte order marker, because it would be far too easy to define that. Yes, we always use the first byte is the one with the higher information, and the second byte is the one with the lower information. That's how we would see it. No, it's sometimes this way, sometimes the other way. So we need some information at the beginning of the text to know which way around we have to turn the bytes. And if I have something that is not in the first plane, I need the supplementary characters. The supplementary characters are those 8 boxes I've shown you, because now we need to do some weird maths, some bit maths. So sorry, but we have to dig deep into bits and bytes here. If I want to encode this emoji, which clearly is not on the first plane, I need to do some magic. The first thing they do is they subtract this byte mask from the character mask, from the character definition. So instead of 01F602, we now have 00F602. Of course, we can't use the F602 because that's a completely different character. So what do we do? Oh, that's the binary representation here of this F602. So now we take the D8, D800, and at the first 10 bit of this, so 0000, 1111, 01, we add that to the D8. And the second 10 bit we add to DC, which is, well, the first and the 8th, I think, of these gray boxes I've shown you. And then I get two 2-byte sequences, which is D8 3D, DE02. And that is the UTF-16 representation of this emoji. Did you understand that? If you didn't understand it, feel free to come to me later. Feel free to ask a Java developer you know. I'm pretty sure they don't know how it works. Yeah, I know, it's a bit whoop. But I put the slides on later on, so you have always the possibility to check that again. And probably find mistakes I've made in there. So how does that work in UTF-8? It's easy in UTF-8. In UTF-8, we have between 1 and 4 bytes. And therefore, I can handle all those Unicode code points, and we can even handle much, much more. So should the Unicode consortium at one point decide, you know what, 17 planes is cool, but we need more, UTF-8 will say, that's fine. It's mostly used in Linux, mostly used in the web. And it's stream safe. I'll show you later why. You can use a byte order marker, but it's not necessary. And you probably shouldn't use it because it blows up some things. So how does it work? Let's have a look at the single byte. A single byte always starts with a 0 bit. As I said, I'm sorry, but we have to dig into bits and bytes here. And that 0 bit is always followed by the ASCII code. So when I have an ASCII character, it will always be a single byte character in Unicode, in UTF-8. So the A, for example, is 01, lots of O's and a 1. How does that work with the multi-byte character? A multi-byte character always starts with a 1. And then we have a 1 for each follow-up byte in the first byte. Or a 0 for the following. Wait a minute. OK, I'll show you. So this is a single byte character. We have an O, and then we have the payload, the ASCII. This is a 2-byte character. We have 110, and then payload. And then the second byte is 01 and the payload. And how does a 3-byte character, 3-byte sequence look like? 1110, 1010. And you guessed it, 4-byte. Do we need more than 4 bytes? No. But UTF-8 could be even extended up to 7 bytes. So we can translate a lot of characters with that. Yeah, X is the payload. So to give you an example, let's use this funny German umlaut. We have 110 as the identifier for the first byte of a multi-byte sequence. Then we have the payload. Then we have the 10 for the first follow-up byte of this 2-byte sequence, because it says 110, so it's a 2-byte sequence. Awesome. And then we have the payload. And within that payload, we just put in the Unicode encoding, the Unicode information. And what doesn't fit into the first or into the second bit goes into the first one. Perfect. Do you get the picture? Who's not with me? Okay. So I said Unicode is, UTF-8 is stream safe. What do I mean with that? Is that a valid sequence? No, it isn't. So no matter where I intercept a UTF-8 stream, I can always figure out, is this a valid sequence? No, it's not. Let's see the next one. And then I first start displaying information from the first point where it is sensible. Is this a valid sequence? No. Is this a valid sequence? All these will result in this weird character. So there is a safety built in right into UTF-8. So we're finished with the basics. Cool. Who's still with me? Whose head smokes? Okay, cool. Well, the code part is pretty easy. Always use UTF-8. Use UTF-8 in your source code files. If you have the possibility, make sure your source code files are stored as UTF-8. Nothing is worse than using UTF-8 everywhere and then having your source code file in ISO 8859, whatever weird character set you want to use. Set your default char set in your PHP-ini to Unicode, to UTF-8, of course, not something else. Put a content type header into your server files, into your HTML files, wherever. Set an accept char set header. Use within your form information, use accept char set UTF-8, so no one will be able to, well, put in some weird characters in a weird character set. And use the iconv or the MB string extensions. And please mind your locale settings. You shouldn't change them on runtime, because changing the locale setting will change the locale setting for the whole, at least if you're using the Apache module, it will set the locale settings for your whole module. So it might suddenly happen that your locale changes because some other thread changed your locale. Awesome. And try to debug that. Okay. How do we convert to UTF-8? Because what I've shown you was pretty easy, because that's all the information I have as a developer. I can make sure all these settings are set properly. But at one point, we get user input, sadly. Yeah, wouldn't it be much easier without all those users? So no one knows what the user puts in there. They might have a Word file, they just copy and paste, and whoever knows what's in that Word file. I'm not only talking about the content, I'm just talking about the encoding. So the easiest thing is to use MB convert encoding from non-UTF-8, whatever it is, to UTF-8. Yes. Or what I would recommend you to do is use the iconv extension. Who of you has never heard of the iconv extension? Okay. Some. Okay. It's pretty awesome. You can use MB detect encoding. Just put in your string. And it tries to figure out what encoding it is. That might need some tweaking, because the default is not necessarily very sensible, but usually it works pretty well. And then you have that gives you the encoding the text is currently in. And then you can use the iconf extension and tell it, here, this text is in this encoding, and I want it in UTF-8. And here is the text. And it will give you the UTF-8 version of the text. It will convert the text to UTF-8. I usually use the translate and ignore argument as well, which means if you can't find a proper UTF-8 character, try to transliterate it. That's where the locale settings come into play. Because transliteration means if I have an Ä, German Umlaut, and I have the German locale, it will transliterate that into AE. If I have the American locale, it will transliterate it to A. But no matter what, it will transliterate it to something sensible. Sometimes you get text where some characters are just mixed up. It doesn't work to convert them automatically. And that's where ignore comes into play. As soon as the iconf library stumbles upon a character that it just can't convert, it usually just throws up and tells you know what? At that character position, there is something wrong. But if I say ignore, it just silently ignores that, throws it away, and takes the next character. So yes, you might have data loss, but it will not interrupt your workflow. For me, that was always the perfect solution, to just ignore that. It depends on what you're doing. Yeah.
Somehow feedback that something was ignored?
I'm not sure on that. Let's discuss that later. I think you can, actually. For me, that was never important. That's why I never dug into that. Oh, okay. Okay, so take care. There are two functions in PHP that I call UTF-8 decode and UTF-8 encode. Their name is awesome. Don't use them. Huh? Because they only convert from ISO 8859.1 to UTF-8. As soon as you have something completely different than the ISO, it will not work. So for almost every string function, there is also an MB string function. Use them. Makes your life much easier. If I have this weird calculation up there, and I try to convert that into binary, I get this string. And yes, I see there is a 3-byte sequence, then 3 1-byte sequences, a 3-byte sequence, 3 1-byte sequences, and a 3-byte sequence. If I use string length, of course I get 18, because string length is not the length of the string, but how many bytes are in that string. If I use the MB string length, I get the correct information. Yes, it's 9 characters. There's also grapheme functions. Oh, I mixed something up there. Well, okay. Anyway, if I have this family emoji, and I do the bin to hex, I get a really long string there. That is the binary representation of this one emoji up there. And when I use the MB string length function, I get 7. 7? That's just 1. No, actually it's 7. Actually it's a man emoji, a woman emoji, a male child, a female child emoji, and a male child emoji, 4 emojis, all with a combination character in between. So I have 4 for the emojis and 3 for the combination characters, gives me 7. If I use the echo grapheme string length, I get what I'd expect, 1. Interesting thing is, if you use that emoji and paste it into the terminal, you might actually get those 4 emojis with some weird characters in between. And I had, at one point, in one application, I pasted that emoji in, and then I said, no, I don't want that. I want something different. And I hit my backspace. And suddenly it was just a family of 3. And then I hit backspace, and it was just a couple, which shows you how it is interpreted internally. That's pretty awesome. So, who knows what function overloading is? Don't use it for the string functions. For all those that don't know what function overloading is, don't dig deep into it. In regex, you can use the U modifier. The U modifier is not only necessary if you have an emoji or a UTF-8 character, a Unicode character within your regular expression. It's also relevant if you have something within your string as well. So you should always use the U functionality within your within the regex. Latin 1 as character set and Swedish as collation, you know? Yes, that's what I told you already about the collation, about the sorting. MySQL uses separate encodings for different parts. It uses a different encoding for the server, for the client, for the database, for the table, for the field, and for the connection. Really? If you use a show variables like Characterset, you get all those informations listed. And usually, they're not the same. We might run a bit over time, sorry. Always use the, set the character set of the server to UTF-8. Sorry? I get to that. I've written all UTF-8 here all over, but actually you shouldn't use UTF-8, because UTF-8 internally is UTF-8 for 3 characters, for 3 byte. So you should always use UTF-8 MB4, which is UTF-8 4 byte length, so to say real UTF-8, not MySQL UTF-8. And you can set it when you create a table, or you should set it when you create a table. You should set it when you create your connection. The first thing you pass over a connection is set names UTF-8, MB4, actually. No, I think it's UTF-8 in that case, actually, because, well, MySQL. Sometimes it doesn't work. No, you set it UTF-8, MB4. So we create a new PDO object with that string, and we set the encoding of the connection to UTF-8 MB4. And what happens when you forget the connection? Let's send an A, which is this bit sequence in UTF-8. That's what the client sends. So the client takes that and puts it into the connection. Perfect. But we forgot to set the connections encoding. So that's still Latin 1. What happens on the server side? The server says, oh, thank you for giving me those 2 bytes in Latin 1. So I convert them to UTF-8. What do we have in our database? 2 characters. Thank you very much. Yes. Though I have to admit, depending on what you're using, MySQL 8 actually has sensible defaults by now. So they actually use UTF-8 MB4. And depending on what distribution you're using, I think Ubuntu started with 14 or 16 to actually roll out MySQL with proper settings. So they compiled it in the right way. Yeah, short recap, use UTF-8 everywhere. Use the iconv and the MB string extensions. Don't use UTF-8D or encode. Don't use function overloading. Teach your MySQL proper UTF-8. And remember that MySQL by default only uses 3 byte UTF-8. 3 byte UTF-8 is nothing else than 2 byte Unicode. So you can store the first plane of Unicode perfectly. Everything else just gets garbled. Well, never appears anywhere. It's silently ignored. Yes, I would like some feedback. But first, do you have any questions? Yes?
If there are 17 planes,
yeah.
What are on all those 16 other planes?
As I said, Unicode tries to handle all languages, all characters from all languages, and especially all historic languages. So most things on the other planes than the first one, apart from the emojis, is very interesting for archaeologists or historics or people like that, you won't encounter most of that. But as the emojis are on those pages as well, and you know what users will put into your text fields, you need to remember that. Thank you very much.